So we have discussed about insertion operation, insertion in a linear linked list, correct? We have seen that when we are going to insert, there are basically three different positions. One is insert at the front, insert at the last or end, and insert at any position, any given position. Okay. Similarly, and remember one thing, that this is the case when we are going to insert at the front, our head will be modified. Head will be modified. So we have to take care of this case separately. Now today we will start with deletion. So similar like insertion, we can delete any particular element, positional element, but I always prefer deletion of a particular element, not particular position. I am asking to delete a particular element. It means the first thing that you have to do to delete a particular element, you have to search it. So first thing is you have to search that element, correct, whether it is present or not. Then after searching, delete. Again, delete means delete the data or element, whatever element, by modifying the addresses. So this is the logic. For insertion, you have to take care the position. After getting the proper position, the meaning of getting proper position means you have to set a pointer variable properly, where means the node after which you are going to insert, and then you have to modify the addresses. Similarly, in case of deletion, the first thing that you have to do, you have to search a particular element, and after getting it, after searching, when you are sure that the element is present, then you have to delete it by modifying the address. So if I want to represent it in a pictorial form, the pictorial form will be like this. So this is my head pointer, okay, this is pointing to the first node, then comes the second node, then comes the third node. Okay, so this is my linear linked list. Let us assume the elements are this one 5, this one 3, this one 7. Okay, suppose I am asked to delete, so this is the element that I need to delete, and I have entered say 5 here. So I have entered 5 here. So it means my search element is 5. If I found the element, then what I will do, I will delete it. It means, so here the element that I am going to search is at the front, So if I delete this particular node, then obviously H will point to the next node, and this part must be deleted. Now here deletion means not only changing the address, also you have to remember that you have to free the memory. Why? Because we are allocating memory. Whatever we are doing in case of linked list, we are using dynamic memory allocation, and we know dynamic memory allocation is actually done in heap memory. So after deletion, it is not only changing the address or separating the node from the linked list, but also you have to finally free the memory, so that in other process it can be utilized. So that's why you have to free the memory space. Okay, so the technique is very simple. Just you have to search for a particular element. If you found that element, you have to point, the previous node or pointer which is pointing to that particular node will point to the next. So far H is pointing to this, and this is my search element. Okay, so this H will point to the next. So I have to do this simple thing. So the technique is pretty simple. So we are starting with a pointer variable. We are calling it current pointer. So here you can do it with single pointer, but better you use two different pointers. One is a current pointer, and let us assume another is a previous pointer. So I am using two different pointer variables. Okay, what is the initial value of these two pointers? The current pointer is pointing to the first node where head is pointing, and previous, since previous is not in pointing to the linked close, so it is previous to the current node, so initialize it with null value. So the picture will be like this. The picture will be like this, that just take another color, suppose this. So the P and H is like this, so sorry, P and C is like this. So C is pointing, C is the current pointer, C is pointing to this node. Okay, and P is now pointing to null, so this is P. So C means current pointer, P means, sorry, previous pointer. So this is the initial position of these two pointers. Next, what we have to do, using this current pointer, my logic is to check the data with my search element. Okay, so this current pointer will be used to completely traverse the linked list. So current not equal to null. Until current becomes null, we have to do this. Okay, then what I have to do, I have to compare the current data. Current data means current arrow dt, whether it is equal to x or not. So I am simply going for a search operation. Okay, now if my search element is there, if my x is the current data, then what I have to do, I have to delete that particular node. Now see, in this deletion there will be two different cases. One is this one, where the front node is your desired search element. Now in another case it may happen that there is the first node, this is the second node, then this is the third node. Okay, so this is H is pointing to the first node. There is some data values, this is 5, this is 3, this is 7. Suppose my search element is 3. Okay, then my current pointer is initially in this position. Okay, and my previous is initially in this position. It means it is now null, pointing to null. So I will compare my current data with my search element. Is it match? No. So what I will do, I will move forward. Previous will come into the position of current, and current will move to the next node. Again, previous will come to the position of current, so I have to do this first, then current will be moved to the next node. So these two operation I have to perform. Okay, it means previous will move into current, means previous will be initialized with the current value, and current will move to the next node, means how to reach to the next node, by we already know that T equal to T arrow LK, here C equal to C arrow LK will move forward to the next node. So in next iteration C will be in this position and P will be in this position, correct? Now again this data 3 will be compared with the search element. If now it is matched, so what we have to do, we have to delete this particular node. Okay, so it means this will point to the next node, then this will be separated. So how we can access this particular location, now see, since P is pointing to this particular notation node, so what is the name of this? The name of this is P arrow LK. Okay, so we have to modify P arrow LK. So far this P arrow LK is holding the address of this one. Now I have to modify this with the address of this node. Now see, where is the address of this node? The address of this node 7 is now in this position. What is the name of this position? The name of this position is CROLK. It means we have to modify the PROLK with the value of CROLK. It means this value, this particular value now copied into this position. It means this is now pointing to this. Okay. Now after this, since I have told you that you have to free the memory. Now see, C is the pointer which is pointing to the node which is separated from the linked list. So we have to free this particular memory which is pointed by C. So after this, what we have to do, we have to free the pointer where C is pointing. So this is the thing that you have to do when there is a deletion in any other position. Now if there is a deletion at the front, then what we have to do, here head will be modified. So whenever there is a head modification, we have to separate that case. Okay, how head will be modified? Head will be modified means H equal to HROLK, or you have to write H equal to CROLK, whatever. Both these two are same. Okay, so if your desired node is at the front position, then you have to modify your head. So it means you have to check whether your desired node is at the front or not. How can you do this? So there are two different technique you can use in to check whether the node that you are searching is at the front, the value you are searching is at the front node or in any other node. By the value of previous one, another is by the value of H. See, if previous is, what is the initial value of previous? Null. If your data is found, see, if your data is found at this position, then previous still in the value of null. So from the value of previous, we can check whether my element found. So this is the case where my element is found. Now element may be found at the front or any other position. If it is found at the front, then you have to modify your age. So we are going to separate this case. So to check whether it is found at the front, you can either check it by this value, whether previous is equal to null or not. Okay, or you can write it like this: if H equal to current. See, when your data is at the front, then both H and current pointer will point to the same node. If both having the same address, then also we can do the same thing, or we can consider, or we can guarantee that the node, that my search element is at the front node. Okay, so if this is the front node case, what you have to do, you have to modify your H, either H equal to HROLK you can write, or you can write H equal to CROLK, any one of them. And after that, what you have to do, you have to free the memory which is pointed by C, because this is the desired node you are going to delete. So this is for what? For front deletion. Okay, front deletion. If this is not happening, if this two cases means the node is not at the front position, then what we have to do, we have already written it, we have to do this one, okay. So if my data is not matched, the else part of this particular if, what happened? First I am going to write this. Okay, if my data is not found, then I will move forward. So in else, what I will write? I will write previous will come into the position of current, and current will move into the next node. Current arrow LK. This is the movement of the pointer, two pointers, previous and current. Now if in the next iteration my data is matched, it is not in at the front node, then this is the else part, and in else part what we have to do, we will write it like this: PROLK equal to, sorry, not PROLK, it is previous arrow LK equal to current arrow LK, and after that free the pointer current. আমি এখানে একটু ভুল লিখে দিয়েছি, এটাও কারেন্ট, যেহেতু আমি কারেন্ট লিখে করছি কারেন্টই লিখবো, এটাও কারেন্ট হবে, সরি। ওকে, so this is the else part of this. Now see, this free is common to both this else part, so I can both this if and else, so I can remove this two from if else, and I am writing it, generalizing it into this position. So this is the uh, uh, deletion of a particular element. Now see, in this particular case, what may happen, that suppose your search data is not present. Suppose your search data is not present, then what you have to do, you should mention that not found. So how can we do this? Either using a flag variable you can use. If there is a modification, if there is a data match, in this case I will modify the flag variable to 1. You can do it like this. So initially flag variable is 0, and after that, after coming out from this while loop, we'll just check whether flag variable is 0 or not. If flag variable is 0, his value is not modified, then here you can write printf element not found. You can write it like this. Okay, so this is the simple deletion operation where we are searching a particular element and then we are deleting that particular node. So another way you can also do it, see, if we continue this, here we are continuing this for loop, is this this while loop. So if there are more than one value like 3, suppose in my linked list there are two nodes with value 3, suppose this one and this one. So if we continue this after getting the first match, then it will delete all the 3 elements. But if I want to delete only the first 3 element, then after this free, what I will do, I will use a break statement here. Remember this, and this two things is inside this if, free and then break. If your data is matched and you want to delete only the first matched element, then use a break statement. Otherwise what it will do, it will search for more, and if there is another such element, it will delete it also. Okay, so that's why I am using a break. So it depends on your means problem. If your problem say that you have to search only the first occurrence of that element, then you will go for a break statement. If it is asked to delete all the occurrences of that particular element, then you have to go without break. Okay, so now today's first assignment is like this. It is again pretty simple. The assignment is delete all the even data nodes in a linear linked list. Okay, so it is very simple. What you have to do, you have to check. So you have to check whether your element, and that means element means here current data. So current data, so you have to check whether this current data is even or not. How to check? Modular division 2. If this is equal to 0, then what you have to do, you have to delete. Okay, so delete all the even data nodes in a linear linked list. So just you have to modify this part, you have to modify this one, first you have to obviously create a linear linked list, then you have to perform this part. Here you have to modify whether the element is even or odd. Okay, so this is your first assignment. So this is particular element deletion. You can delete any positional element also by taking the input from the user. So that is a home task. You can do it just like insertion. You can do front deletion, you can do end deletion, you can do any other given position deletion. Okay, but you have to remember this thing. In case of deletion, the Numbering you have to understand. In case of insertion, the numbering is a little bit different, and in case of deletion, numbering is a little bit different. So here, delete the first node means this one, first node. There is the second node, there is the third node. Okay, but in case of insertion, this is the first position, this is the second position, this is the third position. So there is a little bit different in position value. So you can apply the same algorithm that we have used in case of insertion to search for a particular position, and then you can go for deletion. And we have seen that why in case of deletion we require two pointers. See why we require two pointer. One is previous, which is ultimately holding the, see what you have to do in case of deletion, you have to separate one particular node from the linear linked list. So it means that node, the address of the node must be held in a different variable, and the previous node should be pointed by another pointer variable so that it can continue its traversal. Okay, so that's why in case of deletion we required two pointer. One is previous pointer, another is current pointer. See again, finally you have to free the memory. So that current pointer is very much useful for freeing that memory space. Okay, so this is all about deletion. So in last class I have given one program that is reversing a linked list. How many of you done the program reversing a linked list? I want to check it. So remember, if you want to reversing a linked list, then you require three pointers. Okay, it requires three pointers. One is a current pointer, another is a previous pointer, another is a previous pointer. So you require three pointers. One is for traversing the whole array, or sorry, traversing the linked list. P is required to holding the this is for reversing the linked list. Okay, and this is for holding the rest address. So we require three different pointers. Okay, so I hope you have done this reversing a linear linked list. So I'm not going to that. So the next thing that we are going to discuss is sorting. See, sorting is very important in case of linked list, because the normal bubble sort, or if you say selection sort, then you can say quick sort. Okay, the sort techniques which require swapping of data, we don't prefer those sorting techniques in case of our linked list sorting. Okay, why? Now suppose this is one particular node. Okay, this is another particular node, and when we are going to perform any swapping operation, it means suppose there is a data say 5, and there is a data say 3. Okay, so normally in case of bubble sort, what we do, we compare these two adjacent nodes, we compare them, and after comparison, if it is not in order, what we will do, we will interchange them. Suppose I have interchanged these two particular data, so 3 will come here and 5 will come here. Now this is okay for single data nodes. Single data nodes mean where the nodes having only a single data or single information. But if this node having information like this, suppose this node having information of a student, his name, his roll number, and his marks. Okay, so suppose there is two particular nodes. One is having name AA, another is name BB, roll number is say 5, and this is the two different nodes. And I am going to interchange, I am going to sort them, with respect to the roll number, I am going to sort them. Suppose I am going to sort them in descending order. So in this case, they are not in order, not in descending order. So what I will do, I will interchange these two values. So 5 will come here and 3 will come there. So from this, you can easily understand that this is not the correct way to sort this two nodes. Clear? So that's why if there is a single data nodes, then we can go for this type of sorting techniques where we are going to swap the values. But if our node having more than one data, and I am going to sort the linked list with respect to a particular data, and I am going to use the swapping technique, then this is not a good technique. You can easily understood from this particular example. So which type of sorting we should use in case of linked list? We can use insertion sort. Why? Because in insertion sort, the data which are coming real time, we will put them in its proper position. So suppose this is the first node that we get. This is the first node, new node that we get from user. So suppose this is data is 10. Okay. So this is my linked list, my initial linked list, which is initially null. Clear? Now this is the first node. So first node will be added in this linked list. So after adding this, the picture will be like this: age, the pointer, and this is the first node. Okay. So first node insertion done, no problem. So I have done. I have just modified the address of age. Okay. So first I have to check whether age is null or not. If age is null, then I am confirm that this is the first node that I am going to insert. So next what I will do, I will write it like this. Done. Okay. Now after this, what happened? So now this is another new node. Suppose this is 3. Okay. And I am going to sort them in ascending order. And what is the current position of my linked list? The current position of my linked list is like this. Okay. So I have to insert this. Where I can insert this particular node, since this one having a lower value and I am going to perform a ascending order, so this will be added at the front. So it means this will point to this and this will point to this. It means this node will be added as a front node. Then after adding this, the new linked list picture will be like this. H is pointing to 3 and then 3 is pointing to 10. Okay, done. Now after this, again I am going to insert another data. So what is so suppose this is my new data. Suppose this is 5. Okay, and this is my current picture or current linear linked list, where I have to insert this particular node. Okay, so this is my current picture. So if I insert this node in this particular linked list, then first I have to compare this 5 with 3. 5 is greater than 3, so I will move forward. Now then I will compare with 10. 5 is less than, so where I can insert this 5 in between this 3 and 10. In between this 3 and 10, I can insert this new node 5. So my after insertion, the picture or pointer change will be like this. This will point to this and this will point to this. Then I will get a picture like this. H is pointing to 3, 3 is pointing to 5, and 5 is pointing to 10. So this becomes the new sorted linked list. So in this way, when we are creating, means at the time of creation, we are sorting the linked list, linear linked list, using insertion sort concept, insertion sort concept. Okay, this is one way. Now suppose, so when I will go for this type of sorting, now see, if I want to represent any polynomial equation, so I'm just asking that the situation where we require this type of sorting means at the time of creation we have to sort them. Suppose I'm going to represent any polynomial equation. Polynomial equation generally represented in this form: 4x to the power 5 plus 3x cube plus 2x plus 5 equal to 0. Suppose this is a polynomial equation. Now, if I represent them in a linked list format, then it will be like this. It will be like this. Now, in a node, there are two different data, not a single data. There are two different data. See, for a polynomial equation, what are the parameters we have to represent? We have to represent this one, which is called coefficient. Okay, and another parameter is this one, which we call the power. So when we are going to represent any polynomial equation, whether it is for x or y, any variable, we have to represent them with these two parameters. One is coefficient, another is power. It means in this particular node we have two different data parts. One is the coefficient and another is the power. So it will be like this. So my node structure, in normal linear linked list node structure, there is two members. One is the data part, another is the link part. But in polynomial node representation, so in case of polynomial node, my structure will be like this: struct p node. Okay, the first thing is the integer coefficient CF I am writing, then the next thing is integer power PW, and the next thing is the link pointer. So struct p node star LK. So my node structure will be like this, okay, and this is my head pointer which is pointing to the first node. So the picture, the polynomial representation, the linked list representation of this polynomial equation will be like this: 4 and 5, the next one 3, next one 2, 1, next one 5, 0. So this is the polynomial representation, linked list representation of a polynomial equation, poly equation. Okay, this is the representation. Now see, this polynomial equation by default is maintaining one descending order sorting on the power value. See, power value always decreasing: 5, then 3, then 1, like this. So it is always maintaining a descending order on the basis of power. So when we are going to create the polynomial equation, at that time we have to make them sorted. Means suppose first user entered polynomial value 3 and 3, that means coefficient 3, power 3. In next iteration, when I am asking for do you want to create another node, suppose he entered coefficient 4, power 5, then this node will be added at the front of this node. Okay, it means we have to maintain the sorting, and this is the insertion sort. Okay, this is the insertion sort at the time of creation of a linked list. Clear logic? Clear? So we require this type of sorting when we are going to represent linked list, when we are going to represent a polynomial equation with the help of a linked list. Okay, now suppose in another problem where there is already some data and suddenly we require to sort them for better insertion. See, if the data is already in sorted order, then it becomes very easy to insert a new element. Okay, that's why suppose I have a random data, and I have a random data set or random data nodes rather than data sets, random data nodes, and then I am going to sort them. Okay, so if I am going to sort them, then I have to go for a different kind of sorting. Remember, in case of linked list, everything must be done. In case of linked list, there is a very important term. In case of linked list, everything everything should be done. You can do it in another way, but should be done by changing the address. Remember this. It means, what is the purpose of this linear linked list or linked list? The purpose is there are some free memory spaces, there are some free memory spaces, but they are not contiguous, correct? Not contiguous. Now I have to make them continuous. That is the purpose of any linked list. Okay, we are going to join the scattered memories. Okay, scattered memories. So it means when there are different free memory space, if I change the data itself, then this is not the correct linked list representation. What I have to do, I have to change the address. Suppose the picture is like this. There is a data 5 and there is a data 3, and I want the data in ascending order. Then I have to change this address. This will point to this. I have to change only the address part. That is the main logic behind the representation of linked list. Okay, so if there is a random data nodes like this, suppose there is a random data nodes like this, first one 5, then one 10, then suppose 3, then suppose 6, then suppose say 2. Suppose this is a already created linear linked list for my suppose user given the input in this way. Now suddenly I require to sort them. So the first case where I have applied insertion sort, it is sorting at the time of creation, which is required. We have seen one example where we required that type of sorting. But in many cases, it may happen that we have some sort of data, we have created some data, and suddenly we require to sort them. Due to some advantage, we require to sort them. So how to sort them? So try to understand the logic. So this sorting is a little bit different. Data will be as it is. What I have to do, I have to change the addresses. So what is the step? The step is pretty simple. What we have to do, first we have to search the minimum element. Suppose I required ascending order. So first search the minimum element. Okay, first we have to search the minimum element. Searching, you have to do this thing first. So from this linear linked list, I will get this